Welcome everyone, we're glad you've joined us. Today's topic is to share information on a new feature of perception that is going to make it much easier to set up measurements of complex applications for electric drivetrain measurements beyond pure 3 or 6-phase power and efficiency measurements. So let's first look at the current situation. You guys are all familiar with this, I am sure. A simple electric drivetrain. You've got a power source, a frequency inverter, and an electrical machine. For each item in the train, you're measuring power, voltage, and current, computing power from that, and then using those powers to look at efficiencies of individual components as well as the full drivetrain. Traditionally, these type of measurements have been made by a power analyzer. A power analyzer was really designed to make static measurements of a 50 or 60 hertz power grid, and it does this very well. They typically have 4 power channels, support both voltage and current inputs. Some of the higher end models may have up to 7 channels. The higher end models may also have a torque or speed input. The system has very high accuracy for the signals for which it was designed, power grid 50-60 hertz signals. It uses an analog tracking PLL to link up with the inputs, and that's what gives it the extremely high accuracy. It has sample rates of a few hundred kilohertz, which is more than enough to support those static 50-60 hertz signals that it was designed for, and it has lots of analysis for grid type measurements. So it's a great solution for doing power measurements on a power grid. Where you're going to get into limitations is when you start to try to use a power analyzer to do power measurements on PWM drives or complex electrical systems. In those cases, the 4 to 7 channels may not be enough. You may need other inputs besides voltage and current. Also, you're not guaranteed to have a static fundamental frequency that's the same for all the inputs. And in those cases, if your system is dynamically changing and you need to understand what's happening, you need to know that you're still getting accurate measurements and the system is sure of what's going on even during those dynamic load changes. A traditional power analyzer can do limited raw data storage, but it's very time consuming. It usually takes 10 to 30 seconds per data set to download before you can start taking data again. And they don't have analysis for electric machine type applications. So not really a huge surprise. Those systems were not designed for use with PWM drives, and they aren't a great solution for that type of measurement. Now, in addition, we're seeing more and more electric type machines in the market, and there's some unique test requirements that are coming with those. So seeing machines that have more than 3 phases is becoming more and more common. There are some new testing requirements for power measurements under rapidly changing load conditions, such as WLTP testing. Also, we've got, in the interest of saving test time, you're starting to see more motor generator setups. So you've got 2 E-machines that are being set up back to back to save testing time. We're starting to see more integrated subsystems, such as an E-axle, which is a transmission and a motor integrated into a single housing. So it needs to be tested as a whole. 4-wheel drives can have individual motors and transmission on each individual machine, or dual E-axles. And the very complex hybrid drive systems like you find in the Prius require some unique testing capabilities. In general, we're all aware that the world is moving towards wanting shorter and shorter test time. Testing is expensive. If we can shorten it and do it more efficiently, then our companies benefit. Also an interest in seeing the acquisition of electrical, mechanical, and bus signals, all with a single system. Are also starting to see more hardware in the loop systems and wanting data acquisition systems that can integrate into that. And as we see more and more of these complex drives, you've got more dedicated analysis about how those drives work and understanding how to optimize them. So a few examples, components that may need to be measured and have some of these unique testing requirements. A multi-phase machine. What I show here is a 6-phase machine. Some advantages of using 6 phases of power rather than 3. If one phase of the power drops out, the machine can still operate, so you've got some redundancy there. In addition, you can get higher power for the same voltage and current levels. Or you can operate at a lower current level and be able to get the same amount of power out. Multi-level inverters is another example. So wanting to have a single inverter to cover all the power needs in an electric car. It reduces costs, losses, and minimizes the real estate required in the car. But if you want to accurately measure everything that's going on with that inverter, both the output to the electric machine as well as the 40 volt and 12 volt outputs, you need more power channels and special formulas for efficiency. An e-axle I mentioned earlier, here's an example picture, is a transmission and a motor put together in a single housing, so it's measured at a whole. You get the high integration saves costs and reduces real estate in the vehicle. And depending on how that e-axle is integrated, you can have a variety of measurement needs, but usually it's at least 2 torque and speed channels that are required. A pancakey machine reduces torque ripple of the low cylinder count internal combustion engine, or ICE. This can improve your driving experience and reduce the weight of the transmission, which is less weight is always nice in a car. The challenge is that there's such a close coupling between the e-machine and the ICE that you can't directly measure the torque out of the ICE. So it requires some advanced analysis to be able to understand how that system is operating. In the case of an all-wheel drive, you've got 4 inverters and motors that are all operating independently. So to be able to look at the driving behavior or how that system operates as a whole, you've got to have a high channel count and 4 torque and speed channels, in addition to some pretty advanced analysis. A dual e-axle drive, such as you find in the Tesla 3, has 2 e-axles that operate independently, one in the front and one in the back, and that has some unique testing requirements as well. So let's look at the basics of HBM's eDrive system. You've got a scalable mainframe, scalable power analyzer that can support from 3 to 51 power channels and up to 6 torque and speed channels. As you need additional power channels, you simply add additional modules to the mainframe, so it's easily expandable. We also have modules that can support mechanical inputs, such as vibration, temperature. If you want to know some strain, some acceleration, something like that, those signals can be recorded by the same system on the same time scale as your power measurements. We can take the outputs of our system and output them on a real-time bus, such as CAN-FD or EtherCAT, to share those results with the automation system so that you can use the results to then determine what direction the testing goes. The perception software is the software that goes along with the Gen Series mainframe. The picture you see here is 8 monitors that are set up with the perception software displayed, and you can see this particular user has all 8 of these monitors filled with perception screens, giving them information about different pieces of their system under test. There are 2 kind of key properties of our system that make it unique, and the first is digital cycle detection. Rather than using an analog PLL to synchronize up and determine our power calculations, we actually do a digital cycle detection on the input signals. What that means is that as soon as those input signals change, we don't have a waiting time. We instantly see that change and can dynamically tell you how the system is responding. What we do with the cycle detection is actually look for level crossings. So the example you're seeing here, the green trace is a current signal, And the red square wave trace you see is the result of doing a cycle detect on that trace. So we use advanced digital algorithms to do that cycle detect, and the user can decide, do I want my calculation results based on a half cycle, a full cycle, or multiple cycles? And you can go from there. Also, you can choose the cycle detection can be done per power channel, and the cycles can be shared between power blocks. So for example, you can synchronize a DC power calculation with rotational speed so that your efficiency is determined over the same cycle for the entire drivetrain. The other unique piece of our system is the real-time formula database. So we're providing these power results in real time, and the way that we do that is each module in the system has a quad-core DSP on board. So the user can set up calculations. An example is shown here just for some power measurements. You can see line 128 is the instantaneous power of phase 1, which is found simply by multiplying voltage from phase 1 times current of phase 1. And then we find the active power by finding a cycle-based mean over that instantaneous power. We do that for all 3 phases and then sum them to find the total active power. Perception creates the basic power formulas and efficiency formulas automatically based on your configuration. And then the user has the option to also create their own formulas. Those formulas are deployed onto the DSPs of each power analyzer board and then calculated in real time. The way perception works today, we have 9 different configurations the user can select from. So I've got 2 examples shown here. In the upper right is the simple drive line with your power source, your inverter, and your motor with a differential lock coming off the motor, or a more advanced example of a motor generator test where you have 2 independent machines being tested simultaneously. So today the user would just tell perception what type of inputs it's using for each of these situations, and perception automatically creates the formulas and the displays. Very straightforward for those 9 standard applications. The challenge is that many of our users are not working in standard configurations. And so for them, it required more work to set up their own formulas and displays, and we weren't as able to do as much automatically for them. So in today's software, here's just a more detailed example for your simple drive line. What you have in perception are columns, one for the power source, one for the inverter, one for the motor. You tell perception what type of signals you're measuring in each case. It automatically creates the formulas and the displays. But what about when we're measuring a more complex system? And what we've done is add this eDrive, what we call the eDrive creator. So the eDrive creator is really meant to make it possible to do a test on any configuration, any complexity system, and have perception automatically create those basic formulas for you. In the formula, or in the eDrive creator, here's just an example of how our simple drive line would map over to that. So you would create your simple drive line in the eDrive creator, and then based on that, perception's going to automatically create the displays and the meters. So I think rather than continuing to do a PowerPoint, we're just going to switch over and look at the perception software itself. So here, if I say select eDrive application, you can see that we still have our standard configurations that can be selected, and that will go back to the familiar eDrive interface that many of our users know. However, if I instead select the option at the bottom, eDrive Creator, and I'm just going to start from scratch so that we can see how this works. I select my component, and I'm going to give that component a name. So we'll call that our battery. And I've got an output from the battery that's already there automatically. So now I click and say I want to add another component. And this one I'm going to call my inverter. I'm going to add an input connector that connects to the output of the battery. And I'm going to add an output connector as well. Now I add another component that I call the motor. And we'll have an input connector that connects to the inverter and an output component. And then finally, one final component, I need a transmission. And I'll have my input connector that connects to the oops, I did the wrong one, output of the motor. There we go. And I'm actually going to add two output connectors because we're going to have a left wheel and a right wheel. So there's all of my components, and now I can go back in and decide where I'm making measurements as well. So if I click the checkbox that's the entrance to the inverter, I'm going to say I have a DC single phase input power, and I'm going to select the channels I want to use for that. Now I'm going to select the output of the inverter, which I'm also going to measure as 3-phase, phase to artificial star, and I select my channels for that. And then we're also going to measure the output of the transmission. So I'll select there that I have mechanical signals, torque and speed, and select the channels I want to measure that. And one more, torque and speed, and the channels that I want to measure that. So that covers all of my channels. Now the final step would be to add an efficiency. So I click Add Efficiency, and I want to know the efficiency from the input to the inverter and the full output. So I think I've got everything set. If I say Exit Setup Mode, Perception is now creating all of the automatic formulas for me. If I select my inverter, I can see the input, current and voltage, and the 3 phases of output, as well as meters for a variety of parameters related to all the calculations that are taking place. It's very simple to click and pick and choose which items you want to see in that meter display. If I select the transmission, then it changes and shows me all the signals that pertain to that transmission. I can also select the efficiency box, and then I'm going to see those efficiency results as well. So hopefully that gives you an idea of how it looks like, or what it looks like in perception. I'm going to go back to my presentation now. Once you have your system set up, you can also enable efficiency maps. And so you can select over which pieces of your measurement chain you would like to see those maps. And you're able to view multiple maps at each time, simultaneously. So what this example shows is you see an efficiency map for the motor, an efficiency map for the inverter, and an efficiency map for the entire drive. And the user selects the x-axis, y-axis, and z-axis signals based on the calculations that are available. So in a test type situation, this table would build up as you move from set point to set point of your motor. It would slowly fill in one row at a time. And for blocks of that data, say every 10 points or whatever it is, then it would populate this efficiency map in real time. So if we look at a few of our examples and how they would look in that eDrive creator, our dual e-axle now has a battery, 2 inverters, 2 motors, and 2 transmissions. You would build each of those pieces, tell perception where you're measuring, and it's going to create all of those formulas for you automatically. For a full electric, all-wheel drive, you're going to have your battery and then basically 4 individual arms that all look basically the same. But the difference here is the user doesn't have to create the formulas manually. They're going to be done automatically with the eDrive creator. And finally, your hybrid drive with eCVT could look something like this. So in summary, a comparison between the traditional power analyzer and HBM's eDrive system. HBM's eDrive power analyzer can support up to 51 power channels and 6 torque and speed channels in a single mainframe. The traditional power analyzer gives you very high accuracy for static grid type measurements, whereas the HBM power analyzer will give you a high accuracy for all signals, including in dynamic situations. No synchronization is required because we're making all of the measurements in a single mainframe, and the raw data storage happens automatically with no need for download time. You're able to get dynamic results, support fundamental frequencies, other mechanical type signals such as temperature and vibration. We can measure CAN bus signals, and you've got the advanced analysis to really understand what the full system is doing altogether. So the eDrive creator really takes HBM's eDrive power analyzer another step forward in making it even simpler for users to do high-end measurements on complex systems without having to spend a lot of setup time to do things manually. So power results are computed in real time per half cycle, and you get very reliable results for dynamic situations. Raw data is automatically stored, which can come in very useful if you're getting unusual results you don't understand. You can dig back into the raw signals and really see what's leading to those results. The eDrive creator really makes it possible to set up a complex test in a very straightforward way. We have some additional information available on our website. The landing page on our website for our eDrive Power Analyzer is here. This presentation will be shared with you later today, so you'll have that link. And if you scroll down that page, you'll find a variety of other links at the bottom of the page that lead to more information. Well, thanks everyone for joining us, and if you have questions, we'd be glad to take them now.